Okay, so let's move on. We created the time series data. And so right now what we have to do is to upload, I hope you can hear me well, is to upload the precipitation data to the model. Now to do that, we just have to select the precipitation data and select in particular the DSS path name in which we have our data. So to do that, we move into our DSS. Here we select the gauge that we have created. We can also rename it, okay, with a right click. Let's call it like and we need to select on the bottom, as always, once you have selected an element, you have to select the different components of those elements. In particular, in case we have a precipitation time series, we need to select the data source, the units, and the time interval. Now, there are more than one possibility. If we open the data source, we have manual entry, single record HEC DSS, multiple record HEC DSS. In our case, we have a single record DSS for the Takeze catchment. So we just have to select a single record HEC DSS. Okay. After we have selected it, you will see that few more possibilities appear. In particular, you have to select the DSS file name, so the file, the reference file in which we have our precipitation data, and the DSS path name. And I'm going to show you what I mean. So for the DSS file name, it's easy. You just have to click on the folder icon here on the right. And you need to find the DSS file in which you have your precipitation data. In my case, I have in this folder, so you will have it in the training folder material. It is called precip data. So you have to select, first of all, the file, the reference file, and then to select the DSS path name. So also in this case, let's click on the icon here on the right. And you will see that a window similar to what you see opening the DSS files will appear. So what you have to select is the data set, the reference data set that you want to use. So here, as I was telling you, there are all the data set that we used for the different catchment of the Atbara Basin. But right now, what we are doing is the simulation of only the Takeze. So we can select the row number 9, that is, as you can see in part A, in part B, the Takeze dataset. Okay, so after we have selected it, we click on Set Path Name. And after we have done it, you see that the writings are in blue, and if you remember, it means that it has not been saved yet. Okay, so let's save it here on the top, as always, with this icon, Save Current Project. And you see that right now it is in yellow because it's not inside the model folder. But you see that right now you cannot select the time interval because the time interval is dependent on the time interval of your dataset. Okay, so here, for example, we have a 1-day dataset, and so the time interval is 1 day. So we have uploaded the precipitation. What we are missing, if we go back into the presentation, is, for example, to set the time window of our precipitation. It is not something that you have to do, but it is something that it is necessary in order, if you want, to visualize in HMS, okay, the precipitation table and the precipitation graph. So it is necessary in order to visualize in HMS what you can visualize in DSS view. Let's do a really quick example. We go back here. You see that right now that we have uploaded our precipitation data, we can open also the Takedze gauge, and you see this new button, this new element that you can select. By selecting it, you can now set the start date and end date of your data set. Now, if you remember our data set, if you go back in DSS and we open the DSS dataset, start the 31st December 1971 and ends the 30th December of 2023. So we can, for the moment, set this as default time window. So 31st December 1971. The start time is fine at midnight. And the end date is the 30th December 2023. It is in blue. So what we need to do is to save. Okay. And once you have saved it, it means that you have changed the time window of your precipitation date. So right now, if we move from time windows to table, you will see exactly the table, so all the values that you have in your data set. Is exactly what you can visualize in HMS if you open the table. Same things for, instead of the table, the graph. If we click on it, we can visualize the graph of our precipitation time series. And also in this case, it's the exact same things that you can do by opening the graph in DSS view. It's exactly the same thing, but you have it on HMS. Now, setting the time windows doesn't change the fact that your series of data starts in 1970 and ends at the end of 2023. It means that it is used only for a visualization purpose in HMS. What I mean is, if you didn't change the time windows, but for example, you want to do a simulation, okay, that lasts for the entire period, anyway, your data are there and the simulation will run perfectly. So it's just a matter of visualization in HMS. It's a possibility that you have. Okay, I'm going to stop for a few moments, really few moments, because this part was really easy. So that you can let me know if there are questions or problems. I hope you are trying to do it back again on your laptop. And then we can move really quickly to the meteorological model and set the time windows for the simulation and run the simulation so that we can see the results. Please, if you can, give me a feedback also if everything is fine. Okay, Manuel. Really good job. Okay, thanks, Emmanuel. Let us click, please start from where you added the DSS data. Okay, Marnat, I will do it back again. So I think we are more or less here. So if I understood correctly, you were able to add, to create before the break, the new component of the time series precipitation. So we are here in this situation in which a new folder appears and in which you have your precipitation dataset. Now, we have created, let's say, the box, okay, but we don't have yet the precipitation that must be inside the box. So we need to upload our precipitation. Now, we have the DSS, and you can have it too in your training material folder. What we need to do is to select and to connect the HMS to that DSS file. And to do that, if you click on the and select the new gauge precipitation, I call it Takeze because the catchment is the Takeze. You have two possibilities or three possibilities for the data source. So manual entry, it means that you have to manually write down the table with the values of the precipitation. But we already have a DSS view file in which we have all the series of data for the precipitation. So instead of selecting the manual entry data source, we can select the single record HEC DSS. By selecting it, what you will have, what will appear is two new options. The first one is the DSS file name, okay, and the second one is the DSS path name. So we need to select, okay, the dataset that we want to use as a reference. So first of all, let's select the DSS file name by clicking on the folder icons here on the right. And you just have to select the DSS file, okay, that you have in your training manual, in your training folder material. You select it. Only DSS file that you can have in your that you have there, so you cannot be wrong. Once you have selected, we need to set the DSS path name. Also, in this case, we need to click on this icon on the right, select DSS path name, and what will appear is a window that is exactly the same that you have if you open the DSS file. So you need to select from that file the specific dataset that you want to use. Why? Because in our case, we have multiple datasets. That was one for each catchment of the Atbara subbasin. And in our case, we need to select the number 9, that is the Tekeze dataset, series of data. Once you have selected, you just have to set the path name. There is the button in the bottom of the window. Now, as you can see, the right is colored in the blue, and that's because it is not saved yet. So just save it, and you see that right now the colors change. It is in yellow only because the file location is not inside the folder of the model that you have created, of the project that you have created. So if you are going to move it inside the folder, it will become just dark, but it will work anyway. Or at least let's try. Okay, so once we have selected it, what we need to do, what we're missing, okay, let me see. Okay, what we are missing is the time window. We can set a time window. It is not necessary, but you can do it if you want to visualize in HMS the table of your dataset and the graph of your dataset. So in this case, HMS remember the dataset that I gave him. So you just have to change it by looking at the dataset that you have in DSS. And once you have done it, you will be able to visualize the table of data that you have and the graph. That's all. Okay. I hope it was clear enough. Let me know, Marnat, if that was good enough.
Yeah, thank you. Thank you.
That's perfect. Okay. Now we can move to the next step. The next step is the meteorological model. We will go really quickly because it's a really easy one, or at least it's an easy one in the case of the event simulation. What I mean is, remember we have the boundary condition that we need to upload to the basin. Our boundary condition is the precipitation mainly. Now, in case, on the contrary, we are doing a continuous simulation as we have done for the project, there is not only the precipitation, but like boundary condition like the potential evapotranspiration, and if available, also other data such as the radiation and the wind speed. So data that are really necessary in case you want to calculate the, for example, evaporation of the catchment, or for example, the transpiration. In our case, we only have the precipitation. Okay, so it's really simple. What we need to do is to create a new component for the meteorologic model. And what the meteorologic model does for the precipitation is just to connect, okay, the precipitation that we have uploaded to the catchment. So we are using the meteorologic model, the meteorologic component, to tell HMS connect those specific precipitation that I have uploaded with those specific catchment. Now, it's not easy to understand how it works because we are just using, a single catchment, a single precipitation data, a single meteorological model. So it's not immediate, to understand why you have to create a new component just to connect the precipitation with the basin. But try to imagine if instead of a we have multiple catchments, multiple precipitation data, and multiple meteorologic component. In that case, it is essential to let HMS know which precipitation data is assigned to that specific catchment. But right now it's easy, so let's try to do it also in our HMS. What we need to do, as always, is to go on Component menu, Meteorologic Model Manager, and create a new meteorologic component. I don't want to call it model because it's a bit repetition. So I will call it component. So let's create the new meteorologic component. And as always, when we're going to create a new component, you see that here on the top left of the screen, you will have a new folder called Meteorologic Models. If we open it, you see that there is our MET1 meteorologic component. So as I was telling you, what we need to do is just easily connect the precipitation to the catchment. To do that, as you can see, once you have selected the MET1 component, as always, you will have a lot of different options. Also, in this case, if you are curious and you want to check what are these different options for, you can go on the manual, user manuals, and read it. You see there is the meteorologic description. But just by reading them, I think you can understand what they are there for. For example, precipitation, in our case, we need to select a type of precipitation model. The specified hydrograph is our case because we upload a specified hydrograph, but there are a lot of other options. Now, we uploaded a single specified hydrograph, so that can be characteristic of the entire catchment. But for example, the other case that is pretty common is the fact that we have a really big catchment and we have multiple, for example, we want to use the weather station. We have multiple weather stations, okay, scattered all around this catchment. Now, instead of doing an average value of this weather station, what we could do is to use, instead of the specified hydrograph, the inverse distance. So we could upload all those precipitation data, and then HMS, by the using of the inverse distance, will statistically calculate an average precipitation value characteristic of the catchment, depending on the distance of the centroid of the basin to the weather station. Bit complex, but let's say that these are the two main methods. Also in this case, if you're not completely, if it was not so clear, first of all, let me know. Second, remember that there is always the usual manual, okay? So, for example, you can go on precipitation, and here you have the explanation of all these methods. So, for example, you can scroll down until you find the inverse distance. I cannot find it. Okay, inverse distance. And you see that here there is the explanation of how the average precipitation is calculated. Okay, so what we have to do is to select, in our case, the specified hydrograph. We are doing an event simulation, so we don't need anything about temperature, wind speed, or evapotranspiration. And remember, our final purpose is to connect the precipitation to the basin. To do, we need to do two different steps. The first one is to select the basin option here. And you see that what you have to do here is to connect the basin to the meteorologic component. So you need to do, for our basin 1, are we going to include the different, our catchment in this meteorologic component? And here you can select yes or no. Well, to connect our catchment to the meteorologic component, we need, of course, to say yes. Okay, once you have done it, always remember to save. I'm gonna go pretty quick because we're not so late, and in case I will show it again. The second things we need to do is to connect the precipitation to the meteorologic component. And to do that, you see that under MET1, if you open it, there is a specified hydrograph, that is the selected method that we have used, in which we need to select the gauge, so the precipitation series of data to use to characterize our meteorologic component. Also, in this case, you see, we only have data the precipitation series of data, and so we can select only the precipitation series of data. And once you have done it, save. Remember that here we have only a single precipitation, a single catchment, a single meteorologic component. But imagine to have multiple precipitation and multiple catchment. It will have a long list, okay, of options, each one for every catchment that you have. Because for every catchment that you have, you can apply a different precipitation. So this is how it works, the meteorologic component. Let me stop here a few moments. Here you have all the information in the presentation, okay? So you see, connect the meteorologic model with the basin and connect each basin with the precipitation data. This is exactly what we have done right now. So let's stop here a few moments. Let me know if I need to repeat it, if you have questions, and or if everything is fine. Okay, I don't see any questions. So I hope everything was clear. Okay, we are almost done. We have uploaded the precipitation. We have connected the precipitation to the basin. We can build up our simulation run. We are just missing a few points. The first one is the control specification. It is called control specification. It is called control specification, but it's, let's say, the time window, okay, for the simulation. So in the control specification, we will need to, let me increase the dimension so you can see better. We will just need, okay, to select a start date and an end date of our simulation. And more than that, to select a time step of calculation. It's really easy to create. So if we go back to our HMS, it's just another component. If you remember, let's open the component menu. There is a control specification manager. Also in this case, as we have done for all the other components, we just have to click on it and create a new control specification. You need to set, as always, the name if you want the description and create it. And as we have done until now, once we create a new component, a new folder will appear called control specifications in this case. Inside this folder, there is our control 1 specification, and we need to set the start date and time and end date and time of our simulation. Now, we want to do a event simulation. So let's take the case in which, for example, we want to simulate only a single event of our data set. So for example, we open the DSS view, we open the data set, okay, and let's make the example in which we want to study what happened in, I don't know, May 20, sorry, May 2000, with this precipitation event. Let's zoom a bit more. I don't remember exactly in the pre-made, okay, let's do like this. Let me open the pre-made model so that we use the same data window. And let's see what I selected here as an example. Okay, I selected the event of April 2023. So let me check it. So in this case, we are just doing an example of a precipitation event. It was, sorry, May 2023, correct? April 2023. Okay, so it's this one. It's this one. So in this case, we can start the simulation, for example, the 23rd of April and end, about at the beginning of May. Always remember that this is the time of the precipitation, but we need to consider the fact that the answer of the catchment needs some time. So considering, for example, what we have as the time of concentration that we have calculated before, we have 35 hours. So it means that the raindrop that falls on the faraway point of the catchment will need 35 hours to arrive at the breakpoint. Okay, so 35 hours are 1 day and a half, more or less. So we need to consider at least 2, 3, 4 days after the end of the precipitation event. So let's take the case in which we want to simulate this event. We can stop the simulation about the 5th of May, something like that. I don't remember here. I used the 5th of May. So let's select the time window. It was like, let's do the same so that if somebody of you was not able to follow step by step what we did, can directly open the model, the pre-made model. 23 April 2023, correct? Yes. Start time we can keep 00 and 00. And the end date is the 05 May 2023 at the 00 and 00. Now the time interval. The time interval indicates, okay, if we go back to the presentation, indicates the time step of the calculation of the results that HMS will use. You can set the value that you like depending on the purpose of the simulation and the data available. So what does I mean with the purpose of the simulation data availability and data availability? Purpose of the simulation, it means in this case we are doing an event simulation. So for example, we are trying to simulate a few days of simulation. So maybe if we use just a time step that is like 1 day, is the results will be a lot will be not so smooth. Okay, the hydrogram will be not so smooth. About the data availability, it means that it depends also on what type of data you have. So right now here we have daily data. And so it means that it's no use, like it's no sense to do like 15 minutes print time, 15 minutes time step. So in the pre-made model, I used 1 hour, but we can really use like also 2 hours or like 6 hours, not a problem. Let's try with the 2 hours. So everything is in blue. So always remember to save it. Also because once you save it and the color change, you will see that if something is not working, it will delete what you wrote, but it will change. Okay. So we have set the control, so the time window of the simulation. What does it mean? It means that once we have created the simulation and once we run the simulation will start the 23rd April 2023 and will end the 5th of May 2023. It means that our results will start the 23rd, and will end the 5th of May. with a time step of 2 hours. Okay. Let me stop for a few seconds, and then we can create the simulation and run the simulation and look at the results. Okay, sorry, I have something here I didn't see. Okay, we have the form. Remember to fill it. Thank you, Ambessa. And we have Adele. Please, once, can you highlight again? Sure. What do you want me to highlight? I mean the meteorological components or the control specification?
Yes, Nicola, I think he raised his question since meteorological. Yes, he replied. Thank you.
Okay, yeah. Sorry, Tadele, but I didn't see it. So I can do back again more or less what we did really quickly. I think it's not so difficult. You are following all the instructions, Tadele, so I am sure that you will follow. So I was telling you the meteorologic component is used to connect the precipitation data with the catchment that we have created, that we have extracted. So we need, first of all, to create the meteorologic model, okay, by clicking on, as always, the components menu and meteorologic model. We create the new meteorologic model, and once we have created it, what will happen, as usual, when we create a new component, a new folder will appear here in the browser window. In particular, the new one will be the Meteorologic Models folder. Inside the Meteorologic Models folder, you have a MET1, okay, that is your specific meteorologic component that you have created, in which we need to connect our meteorologic component to the basin. Also in this case, if you select your MET1, there are a lot of different options that you can choose from. All these options are used for the calculations of those processes that regards the interaction between the atmosphere and the ground. So if you read, for example, you have the precipitation, you have the temperature, the wind speed, and the evapotranspiration, so on and so forth. Right now we're doing an event simulation, so if you remember, Tadele, a lot of processes are, let's call it, irrelevant for our simulation purpose, such as, for example, the evaporation and the transpiration, okay? So for the event simulation, what we really need is only the precipitation option. Now, also in this case, the precipitation has multiple possibilities to be calculated. We are in the easiest case, in which we have a single precipitation data that is characteristic of all of the entire subbasin. What I mean is, let's, and I will do the same example again, let's assume that instead of having a single series of precipitation data, we have multiple weather stations that are scattered all around the catchment. Now, how to use them, okay, to characterize the basin? Depending on your purpose, you can, I don't know, use a single weather station, precipitation data, use the closest one to the centroid of your subbasin. You can average data set of all your weather station, or you can, instead of use the specified hydrograph, another option that is pretty common is the inverse distance. Now, the inverse distance is another option that can be used in case you have multiple series of data that calculate an average series of data depending on the location of those weather stations compared to the location of the centroid. So let's say that it calculates an average series of data so that the closest weather station to your centroid will be more influent than the ones that are more far away from your centroid. Okay, but right now let's do something simple. So it's fine to select the specified hydrograph, and what we are missing is the connection of our basin to the meteorologic component. To do that, we need to select the basins options that you have here, and we need to select the connection between your meteorologic component and your basin, your catchment. So you need to select yes. It means when we are doing the simulation, consider the fact that this meteorologic component will work on that specific catchment. What we are missing is the connection of the precipitation with this specified meteorologic component. And to do that, you need to go back here on the browser panel and select the specified hydrograph option that is under your MET1 component. Now here you have a single option. What you have to do is just to select the precipitation data that must be connected to this specific specified hydrograph, to this specific meteorologic component. Now, in our case, we only have uploaded a single series of data, so we will have a single option, and we need to select data case in our case. So I hope it was clear. Let me repeat really quickly also the control specification. The control specification is another component, is our last component that we need to add, and will tell HMS the starting date and end date of the simulation that we want to run. Okay, so we have connected, we have uploaded the boundary condition, we have extracted the basin, we have connected those boundary conditions to the basin. We have set a time window for the simulation. So what we are really missing is the creation of the simulation and the run of the simulation. That's all. So we are almost complete. I hope I hope that it was clear. Let me know. And in the meantime, let's wait a few seconds in case there are some more questions. Okay. Well, in case, just raise your hand and stop me. Okay, let's move back to the presentation. Finally, we can create and run the simulation. Well, we can run the simulation. The creation is really an easy thing. Okay, we have created our control specification. We need to create the simulation run. Now, the simulation run is not considered a component. So we need to do something a bit different from the usual. It is described here in the slides with some screenshot. But let's do it directly on HMS. So we need to go on, instead of component, we need to go on compute. Here we can directly create okay, a simulation run. So by clicking on menu is compute, create compute, simulation run. You see there are a lot of different options for the optimization, the forecast, things. Well, if you're interested on, maybe we can talk about it in the next training in person, but if you're really curious, remember that there is always the user manual. Right now, we don't have time, and it's not part of this training. What we need to do is to create the simulation run. Let me admit Ryan, that is okay. So by clicking on it, what will happen is, first of all, we need to select the name of our simulation. You can select whatever. You can keep it as run 1 because it's the first one. We need to continue by clicking on next. And how does the creation of the simulation works? Okay, you have to select the basin for that specific simulation, catchment of that specific simulation. In our case, we have only a single basin, so the selection is easy. You have to select the meteorologic component to use for that specific simulation. And as you can imagine, what is missing is the control specification component. So the time windows on which the simulation will run. Once you have done it, finish. We have created the simulation run. Also, in this case, consider that this is a really simple model with just a single basin, a single meteorologic component, a single control specification. But imagine if we are doing something more complex, what would have been happen is the presence of multiple basins, the presence of multiple meteorologic component, the presence of multiple control specifications. So the fact that in HMS to connect all these components one to the other is a bit tricky, but has the pros of the possibility to do, let's say, multiple simulation with a single project. Yes, Beer, I see you have your hand raised.
You hear me?
Yes, very well.
Yeah. I just want to show me how in the control specification the starting date and the end date, how you select the starting date and the end date. I want
Sure.
Yeah.
You mean how to well to I think to you mean how to decide which event?
Yeah.
How to select the event? Okay. Okay. Why we selected this type of event is mainly because it's just it's maybe because it's just because it's an example training. Okay. Oh, I see that a lot of people are trying to join. So right now we are doing a training, but let's assume we are trying to we are on a different project, okay? And we have this series of data for our catchment. And the purpose of our project is to simulate a specific event. For example, I don't know, the client is asking us to simulate the event of the, I don't know, 2010, something like that. That occurs in April 2010, May 2010. So what you need to do is to go on the DSS, see your series of data, see when the event starts, more or less, when the event ends, and you set your control specification so that your hydrograph, okay, your precipitation, is inside of those time window. So the important is, let's select a date that happens before the precipitation event, and a date that happened after not only the precipitation event, but after the answer of the catchment. Because the precipitation occurs the 5th of May. But the difference in time from which the precipitation starts and the water arrives, okay, at the breakpoint catchment, the end of our catchment, is different. So this is the, we need to take into consideration the time for the answer of the catchment. That's how you select it. Right now, as I was telling you, yes, Tadela, then I'm coming to you. Right now we are doing a training, so it was just an example, but for the event simulation in general, what you want to do is to use it, for example, if you have a determined return period value. What I mean is, we have this long series of data, and usually what you have to do is to analyze what happened, depending on the study that you have to do, in case of an event, a single event, with a determined return period. So after you have done your analysis of the precipitation, I don't know, with like a Gumbel, something like that, and you have determined, okay, the height of the precipitation with that specific return period, what you can do is to create a data set with those specific event for that return period, and run the simulation of that specific event. So that the results that you will obtain is the hydrograph of for that specific return period event. Okay, so usually it's not used a lot for simulate a specific event that occurs in the past, but it is used mainly, so it is really important. It's something that is it's used also the event simulation for all those specific cases in which you want to know the answer of the basin, or you want to calculate the flow, the effective flow at the end of the catchment, for an event, a precipitation event with a specific return period. So that what you will obtain will be, it's called the design hydrograph. Okay, so the hydrograph that you can use for the scope of your project. I can do also a more specific example, but I don't want to spend too much time. I hope it was clear. Then we have Tadela. How do I select multiple precipitation stations in DSS? I hope I am able to understand your questions. So let's do the example of the Atbara subbasin model that we have developed for this project. What we did is to create the subbasins that you have here at the beginning of the presentation. And you see that there are multiple catchments. In particular, in the Atbara, there was 10 different catchments. And as you can imagine, each one of these catchments has a characteristic precipitation, depending on the morphology of the catchment, depending on, in general, the precipitation data of the catchment itself. So what we had to do is to add and to create more than a single gauge of precipitation. So instead of creating only the Takeze, what we had to do is to go back to component time series data manager and create, for example, a new gauge for the basin. The different catchment is Bougainville, a new one for the second catchment, Urdana, and so on and so forth. So you see that right now you don't have only the Takeze precipitation data, but you have also the precipitation data of different of the other catchments. And as you have done for the Takeze, what you have to do is to change the data source and select the precipitation series of data for the specific catchment. For example, for the Bougainville, you have to select the DSS file. It's always the same, but the dataset is different. And so on and so forth. You do it for all the catchment that you have. Then you have what is different is the fact that in the meteorologic component, you will have to connect not only a single catchment, but you will have to connect all the catchment that you have to the precipitation. I hope I was being able to answer to your question, Tadela. Okay, so if everything was clear, how do I import gridded data? And that's a pretty complex question. You mean gridded data in case, for example, you want to do a inverse distance? And I will show you why we are not doing it today. So here you have the possibility to add the gridded precipitation, but if I have to be honest with you, I never use it. Instead, I used quite a lot. I used quite a lot the inverse distance because inverse distance is pretty useful in case you have reliable weather station and you have, let's say, satellite data, maybe. Yes, sure. Okay, so not the inverse distance. Well, in this case, you have satellite data. The gridded precipitation problem is that HMS is not so friendly user, okay? It means that if you have multiple precipitation data, it's pretty a mess because you have to add manually one by one. Now, I don't know exactly how the gridded precipitation works, but it's pretty complex if I'm not wrong. But let's try to take a look. Here to the, okay, gridded precipitation. Okay, you see that can be used with the most common use of the method is to utilize radar-based precipitation estimates. Okay, now first things first is that you need to use additional software so that it works. So that you can, with the use of this additional software, upload also a grid station derived from the satellite. Plus, if you use this grid precipitation, you need to change also the sub-basin loss and transfer methods, because at that point, you need to use also a gridded loss methodology. So it is really, really complex. And also in this case, what it happened is that it depends on what you have to do. Depends on the scale of your study. Because if you think that you can have good results anyway without using the grid precipitation, as for our project, we can consider anyway the grid precipitation and create an average value, okay, that is characteristic of the single catchment. So yes, you can do it, and it's something that has been added a couple of years ago. I think starting from the version 4.10, and that's why we didn't use it a lot. But it's really complex. It's really complex. So I don't suggest it to you. I mean, I don't suggest it at all, because anyway, the fact of using satellite data without using the gridded method here in HMS can be anyway done by let's say pre-analysis of the satellite data itself with other software. Okay. I hope it was clear. I'm sorry if I was not really able to answer you or to help you. Can I change pixel data to basin average? What do you mean pixel data to basin average? You can switch on your microphone, Tadela, if you like, so that I can help you better. Okay. I don't know if I hope I was being able to help you. Okay, let's move on. We are running a bit out of time. And let's run the simulation. So once we have created the simulation, something that we have already done, what we need to do is to run it. And to do it, we need to select from here the simulation that we have created. It is the run one. And click this small icon button so that we can compute all the elements. It is really fast because, as you can imagine, the simulation is short because it's an event simulation. And anyway, we are using daily data. So we don't have a lot of data that HMS must compute and calculate. So I hope you were able to arrive at this point. If you are not, you can directly open, okay, the pre-made model that you have in the training material folder. And you will see exactly where we are now. I can move on also from here. So we have run our simulation. What we need to do right now is to visualize the results. Now, if we go back to the presentation just to show you that everything it is written also here, there are multiple ways in which you can visualize the results. The first one, that is, let's say, the most, how can I say it? Theoretical one, okay, is to change here from the browser panel. You see that in the bottom of the browser panel, you have three voices: components, compute, and results. So if we switch our browser panel to the results, you see that after you have run the simulation, you will have a simulation runs folder. By opening it, you will see the run one simulation results. And if you click on it, you see these are the results that you have. In particular, in our case, what HMS does is to calculate results for the different element of our catchment. Our catchment was really easy. simple, and so we only have two elements. So we have a global summary, a calibration summary, and the results for our two elements. So let's check really quickly the global summary. If you click on it, you see that there is the information about the simulation times. And then for each one of the elements of your basin, you will have, for example, the drainage area, the peak discharge, and the time in which those peak occurs, plus the total volume. Now, here we are in millimeters, so it's better if we change the units. Now, this is the total volume of water that runs during these days of simulation throughout our basin. We are talking about 770,000 cubic meter multiplied by 1,000. So it's really a lot of water. Now, it is really with this table we can understand, of course, the numbers, but we cannot really have an idea of the shape of the hydrograph with the global summary. So let's try to click on our sub-basin element, and here you have the possibility, first of all, to select a summary table that is more or less has more or less the same information that you have seen before, but with something more, such as the loss volume, the excess volume, and the direct runoff volume. Okay, so there are information about how much water, how much of the precipitation has been lost, if you remember, during the calculation of the loss method. So during the calculation of the SCS curve number method, and how much of these of the effective precipitation transform into the excess volume. Also, in this case, we can see the numbers, but we cannot see the shape of the hydrograph. And to see it, we just have to click on graph instead of summary table. How does the graph works? You see, it is divided into two graphs. The first one in the top is the hydrograph, so the precipitation hydrograph. The one in the bottom is the hydrogram. So hydrograph for the precipitation and hydrogram for the flow. As we can see here, what is really interesting is the fact that, as I was telling you, there is, for example, differences in time, okay, for the peak of the precipitation and the peak of the flow. This delay is the time needed to the catchment to have the answer, to create the answer for the transformation of the precipitation in effective flow. What is really interesting also in the top, if we look at the hydrogram, you see that there is the division into, in blue, you have the precipitation, that is the effective precipitation, and in red, you have the precipitation loss. Okay, all that precipitation that get lost due to infiltration. Okay, I will stop here for a moment. Let me know if you have any questions. Then maybe I can show you other way to visualize the results. And then we can talk about the calibration, try to change a bit the values of our model, and see what happens in case we change the values. Okay, Muna, it's not a problem.
Yes, I've got
let's
an
wait
issue.
a few moments. Yes.
I've got an issue. When running the simulation, I have some errors that one of the errors is saying time for concentration set for benzene 1 is, I don't know, there's an error there. So I have over 3 errors.
Okay. Try to do a screenshot of the errors so that I can see and try to understand how to solve it. Or in case I will let you the opportunity to share the screen so that we can understand better. But if you can give me, okay. Marnat. No time of concentration set for sub-basin 1, no storage coefficient set for sub-basin 1, found 2 errors in basin 1. Okay, it's easy to solve. So I will enlarge a bit so that everybody can see. I didn't tell you, but Marnat helped me. Whenever you launch a simulation, what can happen is that, of course, as for the all the modeling software, you can have some errors that doesn't give to the software the possibility to complete the simulation. In this case, but well, every time that happen, in the error log, that is exactly this portion of the screen that we are looking at, that is this one on the bottom, HMS will give you information about why it was not able to run the simulation. In this case, Marnat has problems with the fact that there is no time of concentration set and there is no storage coefficient set. So it means that when you are doing, sorry, if you remember, the time of concentration and the storage coefficient are the parameters that you need to set for the transform method. Okay, so Marnat, if you go back here to the components and you select your subbasin, your catchment, you remember that we set the variables for the loss method and the transform method. So probably what happened is that for the transform method, you don't have values here. So you don't have values for the time of concentration and the storage coefficient. Probably, I don't know, maybe unfortunately you didn't save it, or I don't know. But what you just have to do to solve the problem, so to solve the issue, is to set the time of concentration and the storage coefficient. It was not something so easy because we used the calculator, if you remember. But in case, you can directly select a time of concentration. If we have all the same catchment, you can select like 35.8. And as storage coefficient, you can select as an initial parameter the same value that you are using for the time of concentration. So, Marnat, let me know.
Yeah, thank you. I went and checked and I found I did not put the time of concentration. So thank you. But the calculation part, I don't know if there will be time to do it again because I did not understand it.
I will try, but I don't know if we will have time. Let me take a note.
Okay, thank you.
Allora, then we have Bayer. I see you have already your hand raised, and you also shared a screen. So here you have two warnings that are colored in pink. So always remember the fact that if you don't have errors, as for example the case of Marnat, it means that the simulation ran. If you have errors, the simulation stopped, and you will not be able to see the result. But if you just have warnings, the simulation will work anyway. We have another one from Tadela. So here the warning is basin map file is missing for basin model basin 1. And the second one is could not connect precipitation gauge to data in the time series manager. Okay. So the last one is probably because we connected the precipitation data, okay, and we selected a file that was not inside the folder of the model. It's just a warning. It means that careful, because if you're going to change the location of your of the folder of your basin, I will have troubles in finding back again the precipitation file that you selected. Sorry. The second one, basin map file, shapefile, is missing for basin model basin 1. So probably here you see this is the shapefile that we selected as a reference, okay, for the selection of the breakpoint. Probably this is a warning that happened. I don't know. Did it happen after you launch the simulation or before? Because I think this could be a warning that happened before you launch the simulation when you opened the model. And this could happen because maybe the location of, I don't know, or the shapefile or something else has been changed. And so the HMS is not able to find anymore this shapefile. It's just a matter of, you know, path. Reference, absolute path and reference path. So probably you are not seeing, if we go here, like this. This reference point that we used for the construction of the basin. But if you have already constructed the basin, if you have already extracted the basin, it's no need to worry about. Okay, so Beira, I hope I was able to answer you.
Yeah, Nico, hello, you hear me?
Yes, yes.
Yeah, the problem is while I'm running the simulation, it's empty. If I don't know if I do not solve these two problems, the running simulation is empty. To make it empty. That's why.
You mean the results?
Yeah, the result is empty.
Okay. Try to make a screenshot of the control specification that you have set if it is empty.
Okay.
And then let's see if that's the problem. This is a warning that I had too, if I'm not wrong. Yes, could not connect precipitation gauge to data in the time series manager, but let's try to run the simulation. Maybe it's creating problem also to me. No, okay. Yeah, this is due to the fact that, as I was telling to your colleague, that we have selected a file that was outside of the model folder, okay? But as you can see, I ran the simulation. I had the exact same warning. I don't know if you can see it, but it's exactly the same. Could not connect precipitation gauge to data in the time series manager. I run the simulation, and you can see that the results, this is another way to show the results. The results are working. So it's not a real problem. If you want to solve it, you just have to move your precipitation data inside, for example, you can put it inside the data folder of your model. Okay, so we have just half an hour. I think it's enough. I don't know if we will have time to see back again the time of concentration calculation, but we will try. So I hope everything was clear, and I hope that we were able to solve these small problems. We were here at the visualization of the results. If you don't have any other questions, I can show you really quickly how to visualize, other ways to visualize the results. The first one I already showed you before without wanting to. And the way is really simple one. Okay, see that Ryan was able to run perfectly the simulation. Thanks, Ryan. You are always perfect on time. The other way is to directly right-click, okay, on the element of which you want to show the results. So if you right-click, for example, on your catchment, let's zoom in a bit so that you can see better. Just right-click on it, and there is this possibility to view the results of the run one simulation. Also, in this case, you can select three different ways. The first one is the graph, and what happened is exactly the same. It to appear exactly the same graph that we have seen a few moments ago. Then we have the possibility to visualize this summary table, that is the one that we were looking at before the graph, and also the time series table. The time series table is just the table with all the results of the simulation. In this case, I used a time step of calculation of 1 hour. And it is interesting to see that if you look at, there is one single value every hour. So for every hour, HMS does a calculation and give us a result. Final way to visualize the results, that is probably the most important, is to visualize the results directly in the folder of the model. What I mean is, if you look inside the folder in which you have created your project, in this case, you can also directly see what is happening inside the folder of the pre-made model. What is happening is that after you launch the simulation run, two new DSS view files will appear. The first one is called with the meteorologic component that you have selected. So in this case, I call my meteorologic component met1. So I will have a met1.dss file. Same things for the simulation. HMS will create a DSS view called with the same name of the simulation that I have selected. So in this case, I have run1.dss. Let's open first the met1. In the met1, you will have really easily just the information about, as you can imagine, the precipitation that you have used. So in this case, if you look at, I don't know if I can zoom in, unfortunately not. So I hope it is visible, but you can open directly your DSS, the DSS file that you have in your folder so that you can see. You can see that there are information only about the precipitation. So you have the accumulation of the precipitation, and it's called precipitation ink. It means if you open the graph, it's exactly the hydrograph that we used for our model. While the accumulation of the precipitation is just accumulation. Careful, you see that in part D, there is the time window that we have selected in our control specification. So here you have only what you have used for your simulation. So the few days of the event simulation. More interesting is the run1.dss file. Because if we open it, you see that there are, in the part C, a lot of different variables that has been calculated. Now, the real problem is that here we have a lot of different values, but a lot of different of these variables is equal to 0, okay? Because, for example, we have the ET canopy, so the evapotranspiration of the vegetation. We have the potential evapotranspiration, and a lot of, you see that is 0. All these variable has been calculated by, default. But in our case, we just did an event simulation, so all these variable didn't occur, and that's why the results are 0. But it's really interesting anyway, because if we select the flow, you see part C flow of, for example, the basin S1, we have exactly what we were looking at in HMS. This is the hydrogram of our catchment. Why it's more interesting than by just looking at HMS, because as you know, you have done the DSS view training. What you have in DSS can be, first of all, export in Excel. So you can open the Excel, and then here you have all your data that you can put on a report from that you can use to create, I don't know, a graph here in Excel, whatever you like. Second is that you can work with this data. Because maybe you want to do, I don't know, the average values of something, or something like that. The maximum values. That's why this is really interesting, you know, the fact that what HMS does is to create a result in a DSS view. Now, we are missing only 20 minutes, so I hope it was clear. I just show you how to, different methods to visualize the results. I see also Emmanuel was able to run the simulation. Thanks for the feedback. What we're missing is the calibration, because we run the simulation, we pre-select initial parameters to run the simulation, and we have seen the results. So right now what we are missing is a small theoretical part, and then we can try to change a bit the values that we have used as initial parameters to see how these values changes the results. Okay, here you have in the presentation exactly what I explained you, how to the different ways, you know, to visualize the results. And what we are missing is the calibration and validation. So a really brief excursus, theoretical excursus about what is the calibration process and what is the validation. Remember that we are talking about modeling. So we are talking about trying to represent the reality. So we are talking about trying to obtain results of our simulation that are the most similar as possible to unobserved data. So once we have run our first simulation, HMS give us the possibility, unfortunately we cannot do it right now, but I hope we will be able to do something similar in the in-person training, give us the possibility to compare the results that we have obtained with some observed data. In our case, the observed data that were present were some flow station that were installed on the streamline that we can use, okay, to create a comparison and to create a calibration process for our model. So if you see, the calibration is the variation of the parameters of our initial parameters that we have estimated, so that at the end of the day, the result is that we obtain is most similar to the flow of the real basin. So is most similar to the observed data that maybe we can have from the flow stations. And this is a process, okay? Because the calibration is not something that you do just change it once the parameters, because you change one parameters, you see how the changes influences the result. But remember that you have multiple parameters that can be changed, and each one of these parameters maybe, and usually, has different effects, different consequences to the results that you obtain from the simulation. I hope it is clear. And so, how does this process works? First of all, well, we have the estimation of the initial parameter, that is something that we have already done. And then we have what it is called the valuation of the goodness of fit. What it means? It means a comparison between the results and the observed data. So unfortunately it is a bit small. What will happen is that once you open the results, you will have also another hydrogram that in this case is the one that is composed by small segment of blue. And you need to check, and that's now we are going to see what, if my hydrogram can be comparable to the one observed. Okay, if our results are good enough to be considered as a representation of the reality. So for each one of the time that I see that my results cannot be considered as compatible with the observed data, what I have to do, in case my goodness of fit is not good enough, what I need to do is to go back to the model, adjust the parameter, so change the values of the parameter, and do again my goodness of fit. This is a process. You continue adjust the parameter, you continue to change the parameter, you see how the different parameters changes and influence the results until your goodness of fit is good enough. once you have done the valuation of the goodness of fit and it is positive, you means that you have validate your model. You have done your validation. So first the calibration process, that is this one. Once you have done the calibration process with the goodness of fit, it means you have the validation of your model. Now, well, we have already done the estimation of the initial parameters, but let's really quickly say again how to do this initial estimation. Well, first of all, we have the boundary conditions that are not estimated, okay, because it's something that usually has been measured, such as the precipitation. But in general, if you are talking about, for example, the infiltration, the land use, the I don't know, the impermeability of the soil, there are multiple ways in which you can do it. The first one that I want to tell you is the remote sensing, that probably here is not written. So let me really quickly change. No, sorry, I cannot. But in general, the first step that you do is the estimation from a remote sensing analysis. So you look at satellite data that can be globally available. For example, about the infiltration, the type of soil, the land use. And then if you have the possibility, it's always better to do a data collection. A data collection, so some field survey for example, the I don't know, infiltration, also in this case, the land use. I don't know, for example, what could be useful in this case, it would be a sort of infiltration test and something that is useful to understand also the type of soil, okay? If that's not possible, what else can be used? The experience, okay? Somebody of you has a lot of experience, at least for some of the areas of the different basins, sub-basins. So in that case, if you have enough experience, what you can do is to do an initial estimation of the parameters directly derived from your experience. About the goodness of fit, what we need to check? What is the most important things to check? Well, first of all, there are like few points that needs to be checked, and then I stop and I will ask if there is something that is not clear. As you can imagine, the visual evaluation of the daily flow. Okay, so we are talking about, we need both in event simulation and in continuous simulation, that one is the one most used if you need to validate a model, because that it gives you the possibility to do the goodness of fit of multiple events at a single time. So first of all, you need to do a to satisfy a visual evaluation, a visual comparison of the daily flow between your results and the data observed. Second, you can do a visual evaluation no more of the daily flow, but of the monthly average flow. So you need to compare both the daily events and the monthly events. And then what is really important is the peak flow, okay? So the maximum flow that occurs, such as the, let's skip for the moment the number 4, such as the timing, the volume, and well, the peak we already tell it. Why we need to check these 3 main variables, timing, volume, and peak? Because if we consider a hydrogram, sorry, hydrograph. I see there are some questions after. Let me finish to explain this, and then let's suppose we are trying to do a goodness of fit of this hydrogram. So what we need to check is, first of all, the volume. The volume is the area of my hydrogram, and the volume is the total volume of water that runs throughout my catchment. So first of all, this needs to be comparable with observed data. So the total water runs throughout my basin must be similar. The second thing is the peak. The peak means the maximum flow, the value of maximum flow. If I have, let's do an example, in this case, 1,000 or I don't know, 2,000, no, it's not 2,000, 1,900 of cubic meter per second, but in reality, I have 1,000 cubic meter per second, it means I am overestimating the peak. So I need to go back, change my parameters so that at the end of the day, my peak will reduce until I have 1,000 cubic meter per second. Of course, same things at the opposite. The second thing, the third thing, the last thing that is really, really important is the timing. So you remember when I was telling you about the answer of the catchment? How much time does the catchment needs to transform the effective precipitation into flow? In this case, if we look at, we are talking about more or less 1 day, something more than 1 day, because the peak of the precipitation occurs the 29, and the peak of the flow occurs the day after. Why it is important to understand the timing of the answer of the catchment? Because if we want to represent the reality, it is important to understand how much time the water needs to arrive at the end of our catchment. So let's assume we are doing a flooding study. It is essential for us to understand how much time does the water needs to arrive at the end of our catchment, at the end of our possible flooding area. So these are the main three things that we need to check. The final things that I skipped is the statistical measures of goodness of fit. So here we have some example of calibration processes. As I was telling you, there are statistical measures, okay, to understand if the goodness of fit is good enough or not. In particular, I'm going to give you some example that we used for the project: the correlation coefficient, the normalized root mean square error, and the Nash Sutcliffe efficiency. All of them measures in different ways if the goodness of fit can give a validation of the models. Okay. Each one of these parameters has a theory behind it, as you can imagine. I don't want to stress you also because we don't have time, unfortunately. But if you just search for them in the internet, there are a lot of studies, a lot of papers, and you can really easily understand how it works. Okay, so let me answer your questions and let me ask if you have any other questions. Then maybe, unfortunately, we are running out of time, so I can show you really quickly what it means changing the parameters and changing the results, and then we are over. We have Mohammed. What if I am working with an UN gauge basin? What do you mean with UN gauge basin? Sorry for my question, but maybe I'm calling it in another way. In the meantime, I see that also Bair was able to run the simulation.
Hello.
Yes.
Yeah, thank you very much. So I meant by this, so if I was working, for example, without any observed data, so I have to do this simulation, for example, for the design purposes or for the assessment purposes or whatsoever, but I have no observed data. So what are the criteria to evaluate the simulation?
That's a really good question, and I can tell you it's something that happened to me quite a lot. For example, I'm working in Somalia, in which there are no observed data about the flow, apart from few stations on the Shabelle and the Juba River. So what happened if I don't have any observed data on which I can that I can use to calibrate my model and to validate my model? Unfortunately, I cannot be sure to. I cannot validate my model. That's a bad answer, I know, but what I can do to increase or at least to create a model that is as reliable as possible, we can say, not validate, but as reliable as possible, is to, well, first of all, try to find multiple sources for the estimation of the initial parameters. Because I was telling here in the presentation that the initial parameters and okay, where is it? Okay, I was telling here and during all this training that I was not scared a lot about the estimation of the initial parameters, but at the same time, if we are in a condition of suggested by Mr. Mohammed, the estimation of the initial parameters became crucial because I don't have the possibility to validate my model. I don't have the possibility to calibrate my model, neither to do a sort of goodness of fit, okay? Because yes, I adjust my parameter, I change my parameters, but with what I am going to compare them? Nothing. So at that point, I cannot validate my model, but I can try to be most reliable as possible by estimating a good initial parameters. And so in that cases, what is really important is to try to find multiple sources for the first estimation of the initial parameters that arrives both from remote sensing and from data collection and experience. So that at least at the end of the day, what I can assume is that the initial estimation of my parameters is good enough to present a model that is not verified, but that can be considered as, how can I say, a good representation of the reality. I will never be able to verify it unless they start installing, for example, flow stations. Or what I can do, and what we did, for example, there in Somalia, is that we did an initial estimation of the parameters based both on remote sensing, both on data collection, both on field survey and experience. And after the construction of these new water points, what we did is the monitoring of the water. That is not usually something that is commonly done, at least in some areas, but it is essential also in that case to collect data, okay, and data that can be used then for the validation of the model. But generally speaking, if you are in this situation, Mohammed, unfortunately, you cannot validate the model. I hope, I was not able to help you, but I think we have the same vision. I see Nehid. Okay, I see probably the about the forms. Okay, unfortunately, we ran out of time. If you have 5 more minutes, I will show you how really quickly modifying these parameters will change the results. And then we can close. Okay, so if we move back to our model, you remember, for example, let's visualize the summary table. Here we have information about the peak discharge, in case it was 1,837. And the discharge volume was 22.09. Let's keep for the moment millimeters, it's not a problem. So just that, let you show how changing the parameters will influence these values. So how changing the parameters will influence the total volume discharge at the breakpoint, and how it will influence also the peak discharge, so the flow, the maximum flow, the peak flow of our hydrogram. So for example, we can select our subbasin and change the famous curve number. So remember, the higher is the curve number, the higher is the impermeability of our catchment. It means that higher is the number and higher will be the total volume of water that will arrive at our breakpoint, that will flow throughout our catchment. So let's do an example. Instead of 79 or 8, I think we used, I don't remember, we can select 90, okay, as an example. So we save back our model and we run again the simulation. That, lucky us, it's really, really fast. If we go back and check again the summary table, what will happen is that instead of, before we had 1,837 of peak discharge, right now we have 3,095 cubic meter per second. So it has increased a lot because we have increased the impermeability of the catchment. Same things for the discharge volume. Before we had 22 and right now we have 39. We almost doubled the peak discharge, and the volume. Okay, if you remember the 3 main parameters to check, we had the volume and we have the peak discharge. And last one, we have the timing. So the timing, let's move back to the 79. If you remember, and as you can understand, the timing can be visible here from the graph. So in this case, the maximum peak flow occurs more or less the 30th of April at 19, so at 7:30 p.m. To influence the timing, what we need to do is to change the parameter of the transform method. So to change, we need to change the time of concentration, so the time that the water needs to reach the breakpoint, so the end of our catchment. So let's do another example. Instead of 35 hours, we can select 50 hours and see what happens. What do you think it will happen? Well, by increasing the time of concentration, we are increasing the time that the water needs to flow throughout the basin. And so the answer of the catchment will occur later on than what we were seeing before. So let's try to run the simulation, and let's try to open again the graph. You see that before we were talking about the 30 of April at 7:30 p.m. Right now, the peak is occurring the 1st of May at 5:30 a.m. So about 10 hours later. So well, there are a lot of different things that we need to talk about, that we could talk about the calibration. Unfortunately, here we are doing just an event simulation, okay? So there are not a lot of different parameters that can be changed. We don't have we don't have observed data from which we can really calibrate and validate our model. But remember that, at the contrary, during the project, we run a continuous simulation, not only of this catchment, but of the entire subbasins, and there are some flow stations from which we were able to do, as you can see here, the calibration of the models. Calibration of the model test has been done also with the different coefficients, and that we will able to see probably during the next step. So during the next 2 days of HMS training in person. Right now, what we wanted to let you know is the basis of HMS, but so that you know what there will be probably in the next 2 days of in-person training that will occur in the following month. We will try to perform a continuous simulation. Continuous simulation that, as I have already told you, considers different processes, more processes, such as the evaporation, the transpiration, and so on and so forth. And so depends on other variables that right now for the event simulation. And in particular, we will be using the SMA methodology. So it's called the soil MOSID accounting methodology for the loss method instead of the soil conservation services. And as you can see, I'm just putting here a scheme of how this SMA methodology works. Is a lot more complex than what we used here during these 2 days for this event simulation. Okay. Okay, so I think I can close here. Let's have, okay, see, Ryan was able also to try to do some changes to the calibration. I'm going to give you like a few minutes for possible questions or doubts that you have. In case, I don't remember who asked about the time of concentration. We can have, and if somebody want to stay here, we can have like a few more minutes about the explanation of how the time of concentration has been calculated. But apart from that, then I think we can close these 2 days trainings about HMS.
Yes, Nicola, I'm here.
Yes, ma'am.
I'm back again. Thank you, Nicola. I don't know. Do you have finished, or there are some minutes you want to?
No, I was just waiting in case some of the participants has some questions. I know that I don't remember who, but they asked before if there was the possibility to repeat at least the procedure to calculate the time of concentration. So in case somebody wants to stay and listen, I can spend a few more minutes about it. Otherwise, yes, I think we can close.
Yeah, thank you so much. Before you close, I want just to announce that I think there will be some adjustment in the upcoming session, the adjustment in the date of the training upcoming session. So I will keep you updated with any change in the time or the date. So please follow your email frequently for this issue. Yeah, Nicola, on behalf of the participants and on behalf of Intro, I want to convey our grateful for your, effort in conducting this workshop. This training session. It was very enjoyable, very interesting, and I'd like to appreciate all the comments from the participants and their feedback and their questions. So thank you so much for all of the participants for their patience. And yes, this is from my side. And I think there are some hands raised. So by this, I can just say goodbye for everyone, and you can, for everyone who want to ask some questions or who want to repeat from Nicola to repeat a certain process, you are welcome. Thank you so much.
Thank you. Please, I see Ambessa.
Yeah. I just want to make the usual remark about the completing the participants form list. Please don't forget to fill out your details. And thank you so much.
You're welcome. So I think we can here. I see that also Marnata that asked about the time of concentration said that he will watch the recording later. Yes, about the recording, remember that I think the recording of yesterday are uploaded, so you can already see them, and the recordings of today will be uploaded between today and tomorrow, I think. Okay, so thanks everybody for your time. HMS is not like an easy software. I think you will you saw the difference between, for example, something that is a bit more easy than HMS, like I don't know, QGIS, that is more, let's say, yeah, easy to understand at least. But I hope I was not. So thanks everybody for participating to this, and I hope to see you next time. Thank you.
Thank you.
Thank you.
Thank you. Thank you. Bye bye.
I'm waiting for the thank you to drop. Can I hear?